Welcome Algebra 2 students to your first factoring video, Factoring Part 1. I have often been known to call factoring the dirty F word of algebra. I do enjoy factoring myself. I know that it isn't always the easiest thing, but I know that we're going to get the hang of it quickly. You're going to remember this very quickly. I don't want you to stress. So first, real quick, let's just point out who are these strange people we're looking at here on the screen. Well, this guy over here, this is Euclid. And Euclid, remember from Euclidean geometry, geometry that you learn in high school, the geometry you guys learned last year, is Euclidean, named for Euclid because he was the guy that put the whole first big giant set of math books together, basically. And then these folks over here, these are the Babylonians. And I guess what I wanted to do is I looked up the history. In 2000 BC, the Babylonians actually knew how to do this. Euclid knew how to do this in 300 BC. And I think it's important to recognize how ancient the mathematics that we're actually learning is. So let's start by doing a quick review of FOIL. Remember FOIL? First, outer, inner, last. FOIL is how we multiply two binomials. So FOIL is, remember, it's how we multiply two binomials. And the reason we use FOIL is that we have to make sure that we get every product that we need to in this particular problem. There's 4 products we need to actually find. The first product would be x times x, so x squared. The outer product would be x times minus 7, so minus 7x. The inner product would be 3 times x, so plus 3x. And then the last product would be plus 3 times minus 7, or minus 21. Combine your like terms for minus 4x, and that's a quick review of FOIL. So factoring, remember, is kind of going backwards from FOIL for some problems. For others, it's noting a pattern that you take advantage of, that you utilize. A nice repeating pattern you can use. And in others still, it's looking for a common factor and factoring that out. So we're going to start with the simplest level, which is factoring out a greatest common factor. So looking at the 3 terms that we have here, we need a greatest common factor. There's going to be a variable portion, and there's going to be a numerical portion. So looking at the numbers, we have 6, we have 12, and we have 3 as the numbers, the not constants in this case, but coefficients in this particular problem. And to find a greatest common factor, I want you to find your smallest of your 3 values. I want you to ask yourself, does that go evenly into the other 2? In this case, yes, it does, so that is part of your GCF. So in your GCF, you will have a 3. Now, for the rest of your greatest common factor, you need to look at the variable terms and look at the highest exponent that they have in common. So here we have a 3 on the C, we have a 2 on the C, and we have a 1 on the C. And the 1, that's the one that they have in common. That's the highest one they have in common. So that's going to be in my GCF, C to the first power. And again, look at the variables looking at the D. We have D to the first, D to the second, D to the first again, and again, D to the first. That's going to be the one that we end up using because that's the one, the least one that they all have in common. So your GCF here is 3CD. And what you're going to do is divide it out by putting it out front. And then you are essentially taking each of those terms up there and dividing off a 3CD. D cancels, one of these C's cancels to give you a 2 there, and then this simplifies to give you 2. So we have 2C squared for the first term. Oh, not 2CD squared. Let me fix that. 2C squared. And then we have a minus 12C squared D squared. Again, dividing. The D and one of the 2 D's cancels. This C and one of these 2 C's cancels. 12 divided by 3 is 4, so minus 4CD. And finally, plus 3CD divided by 3CD. D's cancel, C's cancel, 3's cancel. We're left with a big old 1. And that is your factored form of this particular polynomial, factoring just the GCF out. Excellent. Moving on to factoring a trinomial of the type x squared plus bx plus c. So we'll use a couple of examples for this. Let's use x squared plus 5x plus 6. And we'll start with this one. So what is in the b position? What is in the position of the coefficient of that linear term there? Well, that would be your 5. So b is 5. And what's in the position of the c right here? Well, c is 6. And I want you to remember that what you are doing is finding factors of c that have a sum of b. Okay, factors of c with a sum of b. So I need two numbers that multiply to give me 6, and the same two numbers that are going to add to give me 5. All right, so you think about the factors of 6 that you know, and very quickly you're going to find, oh, 2 times 3, because 2 plus 3 is 5, 2 times 3 is 6. And what you're going to do is go straight to your two binomials. You're going to have x plus 2 for the positive 2 in the pair of factors we found, and x plus 3 for the positive 3 in the pair of factors that we found. Okay, I kind of made myself run out of space there, so I'm going to add another slide, and we're going to do another problem like this one. Okay, how about x squared minus 9x plus 20? So again, we have b, in this case negative 9, minus is a negative, and c positive 20. Factors of 20 that add up to negative 9, minus 4, and minus 5. And there's our factored form. Let's do still another. How about x squared minus 3x minus 28. Okay, b is negative 3, c is negative 28, and again, I want factors of negative 28 that add up to negative 3. Now think just for a moment, remember that you're trying to find opposite sign numbers, so what you really want is for them to have a difference of 3. Anybody find it yet? Negative 7 and positive 4. So this is the second type of factoring, the second easiest, because I definitely think GCF is easiest. Okay, and let's move on to our next type of factoring, which is the difference of squares pattern. So the difference of squares pattern actually is really important. It's going to keep on coming back over and over again in different courses. And you have a squared minus b squared. Okay, difference obviously because it's subtraction, and squares because these are both perfect squares. So the pattern that you have here ends up again two binomials, and it's a sum and a difference of the square roots of the terms there. One sum, one difference. Let's look at a couple of examples. How about x squared minus 49? Well, you find the square root of x squared, which is x. Find the square root of 49, which is 7. And then you put in 1 plus and 1 minus. Now, why does this pattern result in a difference of squares? Let's FOIL it to check. So first, x times x, x squared. Outer, minus 7x. Inner, plus 7x. And then last, minus 49. And you'll see that those two middle terms right there, those two linear terms cancel each other out, and you're left with only x squared minus 49. Let's look at another couple of examples. This time we actually have room. How about 9a squared minus 1? Well, what squared would give me 9a squared? Well, first of all, 3 squared would give me 9, and a times a would give me a squared. So the square root of 9a squared is 3a. And then the square root of 1, well, 1 is a perfect square. The square root of 1 is itself. 1 plus, 1 minus. We're done. That one's factored. All right, how about this one? 64x squared minus 16y squared. Now, before I start factoring this, I should notice there's a GCF there. Well, I can take out that GCF. It's 16, leaving me 4x squared minus 1, and that's almost similar to the one we just did above. So you'd keep your 16 there. Square root of 4x squared would be 2x. Square root of 1 again would be 1. 1 plus, 1 minus, and that's the difference of squares pattern. So I know I'm moving rather quickly, but this is all review from Algebra 1. So this should be relatively easy to start doing as it comes back to you. Continuing on, I think we have 2 more slides. Factoring by grouping. This is the toughest one to see, so I want you to take your time here and I want you to pay attention to what we're doing. Factoring by grouping requires me to first separate my polynomial into 2 groups. The first group has a factor in common, both terms. The second group has a factor in common, both terms. Well, what factor do you see in common in the first pair? Did you say A? Because that first pair has an A in common. What about the second pair? What do they have in common? Did you say D? Because they have a D in common. So now we've got to look at how we actually factor this thing we're looking at. So what you're going to do is you're going to take out what's in common in that first pair. Well, what's in common in that first pair is A. And if I factor out the A, if I take the A and I pull it out front, what am I left with? B plus C. Okay, so I took that A out, and what I was left with was B plus C. Now, look to the next one. We're going to take out that D, and that's going to come out front. So that's going to be a positive D, and what's left in the parentheses, again, B plus C. And that is significant. Yes, the two do match, and they're supposed to. So now what we want to notice is that what we actually have here is A times a value in parentheses plus D times a value in parentheses, and that's kind of similar to saying this. So I replaced the thing in parentheses with a rectangle, and yes, I promise you I have a point here. So what I want you to see is that if I was to take that rectangle and factor that out front, because they both have that in common, just like I did the A and the D here, I can factor out that rectangle, and he can come out front, and what's left in my parentheses but A plus D? Well, I need to replace my rectangle again with what I took out of it, which was B plus C, and check that out. That is exactly what I have when I factor that expression. I know I probably blew up some brains a minute ago, and we will of course do some examples with factor by grouping in class, but this is such an important thing to recognize, trying to see what's going on here. So just to prove it to you real quick, I'm going to FOIL this out. First would be B times A, you put it in alphabetical order, so AB. Outer would be B times D, again, alphabetical order. Inner would be A times C or C times A, we're going to put AC. And last would be C times D. And if you look up at the top, that is the same thing as what we had before, just out of order a little bit. BD and CD at the end, and we got it. Last slide. Okay, so what do we actually use this for? Well, in solving a quadratic equation, we use the zero product property to solve, and it's actually the most efficient and quickest way to solve some of these equations. So let me show you what I mean by the equations we're going to solve. Well, first let's talk about this zero product property thing. If A times B equals 0, then either A has to equal 0 or B has to equal 0. Ooh, it should say or both. Let's fix that. Okay, so now it's if A equals B, then A equals 0, or B equals 0, or both. Now how do we use that? Well, let me show you a couple examples real quick. So we'll do one of each of these types. A squared minus B squared equals 0, and x squared plus bx plus c equals 0, so both a difference of squares one and a trinomial there. And so let me just go ahead and make a couple of these up real quick. Let's do let's do x squared minus 25 equals 0, and let's do x squared minus 6x plus 8 equals 0. So we're going to factor them. So the first is a difference of squares, and we already learned this nice simple pattern. At this point, if you want to, pause it, solve, or at least factor these, and then start up again to see how you finish it. X plus 5x minus 5 for this one. And over here, factors of positive 8 that add up to negative 6 would be minus 4 and minus 2. Okay, so there's the factored format. So again, that zero product property. So right now what I have is I have A, which is this first parentheses, times B, and it equals 0. So what I'm allowed to say is that I can separate these out. X plus 5 equals 0, and x minus 5 equals 0. And I have these two equations that I can now solve by using my simple properties of equality. So this one's x equals negative 5, and this is x equals positive 5. And the solutions for that equation are positive and negative 5. And you can actually put plus or minus right here, like that, or you can list them separately, negative 5, positive 5. Same idea over here. Because parentheses 1 times parentheses 2 is equal to 0, then I can separate them out. And I can have x minus 4 equals 0, and x minus 2 equals 0. Use my property of equality, addition for this one, leaving x equals 4 and x equals 2. And the solutions are 2 and, ooh, that didn't work so well. Oh, it doesn't want to let me erase it. There it goes. My curly braces got a little out of hand. There we go. Curly braces. So that's it. We're going to continue solving quadratics in class. I'll go see if I can peruse, search around, find a funny for you for your very last slide on this one. After some very careful Google searching, I found this for you. I think it's actually brilliant advice, and I really want that poster for my classroom. But anyway, happy factoring. I'll see you in class.